Today we're going to cover enthalpy and steam tables. So when we talk about enthalpy, we want to talk about kind of where this quantity comes from, and we want to introduce some topics such as shaft work and flow work. Okay, so shaft work is work done by moving parts like a turbine. Okay, that could be an axle, turbine, pump. If it's putting energy into the system, that'd be like a pump. If it's extracting energy from the system, that's a turbine. Okay, and then we also have flow work as well. And this is just the work by the fluid to push through the system. Okay, so you have a pump that generates pressure, and it will flow through the system. And the work for flow work is going to be equal to the pressure times the volumetric flow rate out minus the pressure in times the volumetric flow rate in. And so this is due to friction. Okay, so as the fluid flows through the pipe, it has friction with other water molecules and with the pipe walls, and so it is going to require a pressure gradient where pressure in is going to be greater than pressure out. Okay, okay, so that flows through, and enthalpy, the quantity enthalpy, is really just made up for convenience, and we define it as enthalpy equals the internal energy plus P times V, okay, pressure times volume. And we put the hat over it if it's per kilogram or kilogram mole. Okay, now this is commonly used for open systems. So before we had the closed system lecture, but now we're going to be talking today about open systems. So let's just go on to the open system energy balance. Okay, so at steady state, this is these are all of the terms. This is a delta enthalpy per time. Here's the delta kinetic energy, delta potential energy, and then the heat, and then the shaft work. Okay. Now this is the shaft work. Now all of these units are in BTU per hour, joules per second, kilowatt. Those are just changing between different units. When we talk about delta enthalpy change, okay, we can put this in a per mass basis and then multiply by a mass flow rate, like kilograms per second, for example. Okay, and then the delta is going to be the what goes out minus what comes in. Okay, so this is our delta enthalpy change per time. It's going to be a mass flow rate times the specific enthalpies. Okay, so now let's just compare that with the closed system energy balance. Like we had before, here was our closed system energy balance, and this is our open. Okay, open system. And so what are the differences, and where did enthalpy come from? Okay, so before we just had work, okay, right here. But that is equal to the shaft work plus the flow work, and that is equal to the shaft work plus this delta PV, and then we just defined enthalpy as H equals U plus PV. Okay, and so we basically just this equation and this equation, you can they're actually going to be equivalent. We just put them in different forms based on if it's a closed or open system. Okay, so how do you calculate enthalpy? Okay, so there's three things that you can do: tables, equations, or graphs. And so steam tables are always with respect to some reference state. Okay, so it often reports an enthalpy, but really it's a delta enthalpy from a reference value. The tables that we're going to use, the reference value for enthalpy is going to be 0 for liquid water at a triple point. At the triple point, and for water, that's going to be 0.01 degrees Celsius and 0.00611. Okay, so triple point, that's bar. Triple point is where three phases exist altogether: solid, liquid, and vapor. I'll show that to you on a plot in just a little bit. Okay, so if you use data from different tables, you'll need to adjust for the different reference state. Okay, this causes really big errors, so make sure you don't, if you are using different tables, you adjust for that. Okay, enthalpy is also a state property, so it doesn't depend on the path. If you give it a temperature and pressure and look up an enthalpy, that it doesn't matter how it got there, it's always going to be at that enthalpy. Okay, so let's just take a look at this table B5. Okay, now these are the properties of saturated steam. Okay, and this is table B5 is looking it up by temperature. Table B6 will be looking it up by pressure. Okay, but here's our triple point. Okay, that's where our reference point, we call that zero enthalpy, and then we're looking at a change from that. Now, if we cross this boundary, then we also have, for evaporation, we're going to have a change in enthalpy due to going from one state, like liquid, to a vapor, for example. Okay, so there's our delta H of vaporization, and then we also get the vapor pressure. As we look up by temperature, we get a vapor pressure there as well. Okay, so there's our, this is table B5. Okay, and also give you a handout on this just to show you some of the, so you can reference this for your problems. Okay, so that's water, just water and then steam or water vapor. Okay, so liquid water versus the vapor. Okay, and there's the heat of vaporization. Okay, so there's our reference enthalpy. As we saw, that was going to be 0. Okay, and there is our, this last one, that is our vapor pressure. Okay, so let's go on to table B6. Now this one is a little bit different than B5. Now we're looking it up by pressure instead. It's the same information. It goes up to a little bit higher pressures. The other one only goes up to about 1 bar. So if you need to find a higher pressure, you might look in B6 instead. Okay, now this is also saturated steam, same information. And now going on to B7, these are the properties of superheated steam. Okay, so on this side we have liquid, and on this side we have vapor. So now it's not just the saturated liquid or vapor, but we are looking at superheated. Okay, so this would be superheated, and that is also cooled below the bubble point. Okay, and so there is our liquid water. Okay, that's subcooled liquid, and then we also have superheated steam as well. Okay, so this is just when we say things in words, we want to equate that to what that means in terms of variables within our energy balance. So when we say it's well insulated, we just mean that Q equals 0. There's no heat transfer. But that doesn't mean that the temperature can't change. Okay, when we say adiabatic, that means that also Q equals 0, but T is not necessarily equal to 0. Okay, so adiabatic and well insulated, those are kind of the same thing. Okay, isothermal, that just means the temperature doesn't change, but the heat can be put in or taken out. Like let's say you have an endothermic or exothermic reaction, but you want to keep that reactor at the same temperature. That would be isothermal, even though we're removing or adding heat. Okay, so a rigid container, it just means that the volume doesn't change. So the work by the PV work due to pressure change or volume change, that's going to equal 0 for the closed system. Okay, so isochoric, that's also rigid container. That's just a fancy way to say that. That means constant volume, and then no mechanical parts, no moving parts. We just mean that the shaft work is equal to 0. Okay, so no, there's no turbine or pump or things like that going on. Okay, so let's just look at our steam tables. We're going to answer some of these questions right here. Okay, so what is the heat of vaporization at 30 bar? Okay, so let's see if we can, let me just put this over here to the side. Actually, that is not going to let me do that. Okay, so I think what I'm going to do is just come out here, and you can see the answers there. Okay, but let's go ahead and just go through the steam tables and just see if we can work through some of these problems. Okay, so there's just the answers for your reference, but I'm going to show these to you on the tables as well. Okay, so let me just come in here and grab this. Okay, and then I'll come over to my other program here, and let me go ahead and just paste this one in. Okay, so let's take a look at this. What is the heat of vaporization at 30 bar? Okay, so we're going to look, see what the heat of vaporization is at 30 bar. And if I come back over to my steam tables, okay, so I can look up here in table B5 and find, let's see if it goes up to 30 bar. No, it doesn't. It only goes up to 1 bar. Okay, so let me go down to table B6. Okay, now this one is goes up to higher pressures. In fact, we're looking it up by pressure anyway. Okay, so let me go forward on this table to, let's see. Okay, so here we go. This is, the headings don't transfer between these, but here's 30 bar right here, and the heat of vaporization. Okay, the heat of vaporization is over here. Okay, 1793.9, and that is kilojoules per kilogram. Okay, so we found the heat of vaporization, how much energy it takes per kilogram to vaporize water at 30 bar. Okay, so let's go back to our other one now. What is the vapor pressure at 311 degrees Celsius? Okay, again, this is saturated water. We can use table B5 or B6. Let's just see which one. Let's go back there and just take a look at it. Okay, so 311 degrees Celsius. Now these are in Celsius right here, and if I went back to B5, you see that it doesn't go up to a high enough temperature. Okay, so let's go on to B6 and look for 311. Okay, so there it is right here. Okay, there's 311, and we are looking for the vapor pressure. Okay, and so there it is right there, the vapor pressure of water at 311 degrees Celsius. Okay, so if it's 100 bar, water's going to boil at 311 degrees Celsius. Okay, so let's go to the next one. Here we have, what is the specific volume of water at 84 degrees Celsius? Okay, now this one is okay, so 84 degrees Celsius, we can go to table B5 for that. Okay, so let me go back to B5. Okay, so 84 degrees Celsius. Okay, so we have water and steam. Okay, so now this refers to liquid, and that is the vapor. Okay, so 84, there is our meters cubed per kilogram. And then for steam, it's going to occupy a much larger volume per kilogram. So you can see the difference in specific volumes between those two. Okay, so our next one is, what is the enthalpy of water at 200 bar and 100 degrees Celsius? Okay, so enthalpy of water, let me go back here. enthalpy of water at 200 bar and 100 degrees Celsius. Now this one is not saturated, may not be saturated. We don't know that, so we have to go to table B7. Now, okay, so 200 bar, 100 degrees Celsius, and I'm going to go down to table B7. Okay, so let's just take a look at this one again. If we're here, we're going to be liquid. Here it's going to be vapor. Okay, 200 bar. Okay, so let's look here at the pressure. Okay, and as we go down, we'll see there's 200 bar. And saturated, okay, so it'll boil at 365. 365, so we want to look for 100 degrees Celsius, and so here it is right here. So let's just go down this list and over, and then we're going to get to 200 bar and 100 degrees Celsius. So it hasn't, it isn't at its bubble point yet. It is pure liquid. And then as we look at this, we can see that this first number is the enthalpy. The second number is the internal energy, and then the third number is the volume of that, specific volume. Okay, and so we can see here that this enthalpy is 434 kilojoules per kilogram. Okay, so water at 200 bar and 100 degrees Celsius. Okay, so what is the enthalpy of steam at 80 bar and 600 degrees Celsius? Okay, so let's go to 80 bar, and then we have to find 600 degrees Celsius. Okay, so 80 bar, I'm going to need to go over to this next one for higher temperatures. 80 bar, 600. Okay, so there is my enthalpy, 3,640 kilojoules per kilogram. Okay, and then what is the dew point temperature for question number 5? Okay, so 80 bar, 600 degrees Celsius, that's superheated. Okay, and then we could just go back to where it hits the liquid vapor transition. Okay, and then we could interpolate between these two and find out that it's going to be at 295. Okay, so it's going to be between these two. This is where it transitioned to liquid or vapor, or you could go back to table B6. Okay, so let's go back to table B6 and find the pressure of 80 bar. Okay, so here is 80 bar, and we see that it's actually 295. Okay, that's the dew point temperature. Okay, so we could go through a couple more of these, but I'll just go ahead and end it here. Okay, so just use the tables to be able to find these different values. I'm going to go over just a couple additional problems in okay, so a couple different additional examples. Here's a steam turbine. They're very large at these power production companies and plants. But let's say we want to calculate the shaft work, and we know a change in enthalpy, a difference between enthalpy in and enthalpy out. And then we just use our energy balance equation. We have no change in kinetic or potential energy or heat. So it's no heat transferred. And so we just do the enthalpy calculation is just going to be the mass flow rate times the change in enthalpy. So that gives us the shaft work that was done by the fluid. Okay, and that means it's going to be about a 4 kilowatt of generation of power. Okay, so another example is a condenser heat exchanger. In this case, I have steam coming in and then maybe saturated water coming out. Okay, so I'm removing heat from the system. I want to be able to find Q. So we know that enthalpy coming in is going to be 2,875. Coming out is less. We've cooled it down and condensed the water. Okay, so we write our energy balance. Again, kinetic and potential energy are 0. And then also the shaft work, there's no moving parts there, so it's just going to be equal to the heat removed. And so we do a mass flow rate times the change in enthalpy, and let's also just convert it to seconds. And so there we have about 41 kilowatts of energy that is removed from the system. Okay, and that's heat removed. Okay, so just a couple homework hints on 716 and 728.